Group 1 assigned topic, the standard model. Leader, Ms. Gayon. Presenters, Mr. Banyaga, Mr. Agdalapis, Mr. Riotok, Mr. Sison, Mr. Formalejo, Ms. Bayron, Ms. Ronzon, Ms. Rosano, Mr. Fabi, Mr. Lagrosa. Other members, Ms. Cornejo, Ms. Marcuap, Ms. Beter, Ms. Taniedo, and Mr. Palina.
The standard model is the best current theory explaining the universe's basic building blocks. It describes how quarks and leptons form matter and how bosons carry forces that act on them. Do you know that standard model is sometimes regarded as a theory of almost everything? What makes it so powerful? Let's find out. But first, let's explore the key discoveries that laid its foundation.
The Standard Model began in the early 20th century with discoveries like the electron by J.J. Thomson in 1897 and the atomic nucleus by Rutherford. As quantum mechanics developed, Dirac predicted antimatter in the 1930s, leading to the idea of more fundamental particles. In 1961, Sheldon Glashow unified the weak and electromagnetic forces. In 1967, Weinberg and Salang added the Higgs mechanism, explaining how particles gain mass. This was confirmed in 1973 with the discovery of neutral weak current and later the W&Z boson in 1981.
The Standard Model explained three fundamental forces, which are electromagnetic, weak, and strong. Each has a carrier particle, photons, W&Z bosons, and gluons. Matter is made of fermions, divided into quarks and leptons. Quarks form protons and neutrons, while leptons include electrons and neutrinos. The Higgs field is an energy field filling the universe. Particles gain mass by interacting with it. The more interaction, the heavier the particle. The Higgs boson, discovered in 2012, confirmed this theory. Without it, particles would be massless, and life as we know it wouldn't exist. Let's now look at the Standard Model and how particles interact through its chart and diagrams.
Standard Model Chart. This is a standard model chart is categorized on fundamental particles, 12 matter particles, 6 quark and 6 lepton, and 5 force carriers including the photon, gluon, W&Z boson, and the Higgs boson. There are building blocks of the university, each playing a key role in matter and energy interaction. Standard Model Feynman diagram. Here an electron moves right and collides with an electron neutrino moving left. They exchange a neutral Z boson causing the electron to scatter left and the neutrino to scatter right. The Z boson travels briefly between them. This is an example of weak nuclear force at work.
The figure shows the Standard Model Higgs boson production cross-section as a function of the center of mass energy. If the cross-section value is multiplied by the luminosity of the dataset to be analyzed, that is effectively how many Higgs boson are expected to be produced for different LHC energies. The Standard Model Higgs boson decay branching ratios and total width are shown in the figure. You can see that the decay modes change depending on the mass of the Higgs boson. The figure represents how likely the Higgs boson is going to decay into a certain particle or group of particles depending on its mass.
Even though the Standard Model is currently the best description there is of the subatomic world, it does not explain the complete picture. The theory incorporates only 3 out of the 4 fundamental forces, omitting gravity. There are also important questions that it does not answer, such as, what is dark matter? Or, what happened to the antimatter after the Big Bang? Why are there 3 generations of quarks and leptons with such a different mass scale? And more.
The Standard Model isn't just theoretical, it's behind real technologies we use today. For instance, proton therapy used to target cancer cells was developed because of our understanding of particle behavior. Technologies like MRI machines and even parts of your smartphone rely on principles rooted in particle physics. To handle massive amounts of data from particle experiments, physicists at CERN created the World Wide Web. The field also pushed advancement in big data, machine learning, and cloud computing, all of which are now vital in industries, from healthcare to technology. The behavior of particles like electrons and quarks help us understand charge, spin, and energy. These are all essential to semiconductors, electronics, and technologies, like transistors and computer chips, which power modern devices.
Even simple things, light, electricity, and magnetism are described by the standard model. Your phone, Wi-Fi, and microwave all depend on particles and forces the model explains. While it doesn't yet include gravity, it still helps explain much of our physical world. The standard model also explains why the sun shines, how magnetic, and even how lighting works. Particles like photons and electrons are constantly in action around us. Invisible forces made visible through the model's predictions. It's science behind the ordinary.
Imagine the standard model is a finished book with a missing final chapter. What do you think is on the next page? While the standard model explains much, it's incomplete, especially in unifying with the general relativity. Research is focused on new particles and quantum gravity, with endless possibilities ahead. New colliders like the future circular colliders could reveal physics beyond the standard model. Advancements in quantum field theory and AI are speeding discoveries. However, we must consider the ethical and environmental impacts of high-energy experiments.
The standard model shows us the universe is built from tiny, powerful pieces like quarks, leptons, and force carriers working in harmony. It explains much from how stars shine to how your phone works. But the story isn't over. What lies beyond? Maybe dark matter, new particles, or answers to life's biggest mysteries.